Hello and welcome. This is a demonstration for capacitors. I want to show you the circuit that we'll be working with today. It's relatively simple. This circuit has a voltage source, a DC voltage source. That voltage source goes through a push button, and then it's driving a resistor and an LED. Now the resistor is there to limit the current for the LED, and so together we would consider those two elements to be the load. So we would consider this to be the load. And so the push button then is driving the load. So when you push the button, then the load receives current, and then in this case, an LED will light up. So let's take a look at the circuit here. This is the circuit, and what we have is the power supply comes, these red and black wires are the power supply. This is the push button, and it's hard to see the resistor, but it's right here. And then for this, we can turn on our power supply, and just with this basic circuit, if I push the button, then the LED will light up. If I push and hold, the LED stays on. So I just have a way to push this out. Now, imagine that I were going to send Morse code. For example, if I was on a ship with one of the light beacons and you wanted to send a light signal to somebody else, then all I could do is tap out the Morse code. And if anybody can decode that, I would be especially happy. So send me an email if you can figure that out, and I will be forever grateful. So I sent out that message in Morse code. Now, let's say that we wanted to add a capacitor here. So we add a capacitor, and we're going to add a capacitor of varying sizes. Now, when the button is pushed, the capacitor almost instantly charges up. And that is because there's very little resistance through any of these wires. So the capacitor charges instantaneously because the 5-volt power supply has no resistance, and so it charges the capacitor up right away. However, look at when we remove the connection here, when we lift up on the push button, then this circuit is in isolation. So the capacitor will have some energy in here. And so when you push the button, it's going to turn on right away. But when you release the button, the energy stored in this capacitor will have to dissipate, and the capacitor will be kind of like a power supply for a very short period of time. It's like a little miniature temporary battery. So the energy then will continue to move and power this circuit for a short period of time. Okay. Now, the bigger the capacitor, the more energy, the more charge that we have, and so the longer it can run this once the push button is lifted. So today, we have 3 different capacitors that we are going to investigate. The capacitors are a 10 microfarad, 100 microfarad, and 470 microfarad. So just to remind you, I can push this button, and the light will come on. And now let's say that we wanted to put a small capacitor. This is a relatively small capacitor, and we put this over the load, and make sure to look at the light. This is kind of shining on there, so it looks like the light, but we're looking at the LED. See, when I push it and I let it go, it's really hard to tell, but I can still type out my message. And it's pretty intelligible. Let's then move on to a capacitor that's 10 times bigger. This is the 100 microfarad capacitor. And when I put this across the load, it's really shining there. Okay, and so now when I push this and I let it go, it has a little bit of time where it dims out. The capacitor is charged up, and it's still powering this for a short period of time, even when I lift up the button. And it's more noticeable because we have 10 times the capacitance. So imagine now that I wanted to type out my Morse code. And so you can see then that it's much more difficult to distinguish. And I'm not great at Morse code, but if I wanted to type it really fast, you can see that it's kind of forming a limit on the amount of characters per second that I could transmit. And that's because the capacitance is kind of keeping it alive. Now, in the case of Morse code, that's bad. But if you had a noisy power supply, or if you had something that was intermittent and you wanted the light to stay on for a long period of time, or if you wanted to take out the flicker in an LED, this capacitor would be ideal. So a capacitor can be good or it can be bad based on your application. So now, let's take this out, and we're going to go for our BFC here. This is a 470 ohm capacitor, about 5 times as large as the one that we had. And if we take a look at the light now, I'm going to hold it on, now I'll let it go. And you can see this capacitor, once the button is released, the capacitor keeps powering on the LED for a long period of time, or a longer period of time. So now imagine we wanted to type out our Morse code. And you can see it would be very difficult to be able to discern that. If I wanted to communicate, I'd have to go very slow. And if I wanted to go fast, you wouldn't be able to discern what I'm typing, or what I'm keying. And I know you can hear the button going on and off, but if you were only looking at that as a light signal, then you'd have a difficulty discerning what the message would be. So in this case, capacitance is a bad thing. Now I mention this because this was a real problem back in the 1850s and 1900s when telegraphy was the main source of communication. What would happen is that when you run miles and miles of wire, it ends up having a self-inductance. And so the inductance was playing a role a lot like the capacitor in that the keying would kind of smear together, and there was a limitation on the baud rate about the number of messages and the number of dots and dashes they could send at any given time. And so a person who came up with the solution to that was Oliver Heaviside. So Oliver Heaviside was an electrical engineer that does not get very wide recognition. But what Oliver Heaviside came up with was this idea that, well, if we have a very long, and we're talking tens of miles long wire, they have this inductance in them. So he figured out a way to use capacitors every mile or so. So he figured out that, well, if you stick in a capacitor every couple of miles, then you can eliminate that smearing of the dots and dashes, and you can get much more clear communication of the dots and dashes. So not only was Oliver Heaviside a person who fixed a lot with the telegraphy, but he is also the one to have put Maxwell's equations in their present form. So James Clerk Maxwell was very famous in electromagnetics, and he came up with his fundamental laws of electromagnetics that we still use today. But if you ever go back and look at his paper in the mid-19th century, the equations that he came up with were next to unreadable. So it was, they were correct, it was just very difficult to discern them. So it was Oliver Heaviside who came up with the modern form of Maxwell's equations. And when you take your electromagnetics class, even in their present form, Maxwell's equations are pretty difficult, but they would be next to impossible to have in Maxwell's original form. So he made it a lot easier, and you can thank Oliver Heaviside for making your life a little bit easier in a very difficult class. And I want to mention that there's an excellent book, and the book is called Sage in Solitude. It's by IEEE Press. I read this book about 15, 20 years ago, and it is excellent. So all of you electrical and computer engineers should read it. All right, so hopefully that gives you a little bit of insight into capacitors and how capacitors store energy for a short period of time and how they can be advantageous or they can be a disadvantage.